Hello class, welcome back to Introduction to Material Science and Engineering. In this lecture we'll be discussing sustainable design, processing, and sourcing. And for this discussion, which is very short and should be one of the later ones in your course program, for this class we'll be addressing what is known as externalities, or costs beyond the typical boundary conditions considered for cost analysis. And we'll be using that to look at cradle-to-grave or life cycle cost associated with design, use, and retirement of products that we make with our materials. So we can start with asking a question of what drives product cost and what exactly is included in product cost. Well, obviously we have the initial cost, which is basically the sum of the raw materials, transportation from raw material sourcing sites, manufacturing costs, and possibly delivery to final use customers. And that is the market driver typically that determines whether or not it is affordable to manufacture a part or some kind of product. Then we can pan back and look at what's called life cycle costs, which is the cost to society and the environment associated with manufacturing, using, and retiring that same part. And quite often, unfortunately, those costs are much, much higher and frequently delayed. And in many cases and in many parts of the world, the price for those delayed costs are now coming due and really forcing us to take this more holistic view of material design, selection, and use. So we can go on to ask, okay, fine, if life cycle is an important standpoint of consideration for material sourcing and design, what are the components of it? Well, luckily, many of them are the same for what we would consider for just initial cost. You have your raw material synthesis or extraction. You have transportation. There's many steps to transportation, but at the very least, we're going to have some kind of transportation between the raw material synthesis or extraction site and a processing site, and then from processing, assuming there's only one processing step, to market final use. In addition to those necessary transportation steps, we're going to have the energy necessary to process or dispose of the waste, which is quite often not inconsiderable. And again, this is waste disposal just associated with processing. In addition to that, we're going to have disposal, energy and material costs associated with final product retirement, which could be disassembly, burning in a cogeneration plant, partial recycling or downcycling. And we will discuss in this section the role of recycling and its difficulties and ultimate benefits for reducing the overall life cycle cost of any manufactured good. Okay, economic considerations, because unfortunately we're not going to make it in the first place if there isn't money involved. There has to be a basis for economic viability to even have a cost to manufacture something. And one of the benchmark criteria for that is that the price is attractive to customers. If people cannot afford to buy something, if they cannot afford to use it, there is no use making it in the first place. And so that means we have to have a sustainable a sustainable profit for both suppliers and investors. So the people who are supplying raw materials, the people who are investing in the infrastructure at every step in the process, they have to make a living too. So there has to be a net positive in both cases. So we really need to be able to make a profit so that the part that we are designing and manufacturing is actually having a net positive impact on the GDP of whatever nation or global collective that is supplying it. So we have three components for product cost control as materials engineers. We can look at how we design a component, and that basically the geometry, deployment, all of those kind of aspects that are independent of materials and manufacturing. Then we have our material selection, which has been hopefully a large part of what you've heard about in this course, and then the manufacturing methods, which basically are a function of component design and material selection. Those are the big three knobs that we as materials engineers will turn in order to make sure that whatever we make is attractive and is sustainable from an economic standpoint. Then we have to figure in all of the indirect short-term costs that are associated with that: labor, finance, regulation, and these are now becoming very, very significant. Labor always was, and is multifaceted and global. Finance is important if we have to build a new factory, if there is the need for capital equipment, possibly large sourcing changes. And regulation is the new and growing one. At just about every step in our life cycle of material fabrication, we have to deal with regulation associated with, again, the externalities of each of these steps. And quite often the regulatory costs will become the driving ones for any kind of new product design. So that will be something to look for as you go out and start businesses. We can kind of look at all of this from a graphical standpoint, and it's circular because the Earth tends to be a bit of a closed loop system. So if we start with the Earth, and we're looking at sourcing our raw materials, they are going to come from somewhere on the Earth. We will use those for synthesis, primary synthesis, or extraction if we have a mined product, or possibly grown in the case of things like cellulose, precursors to polymers. We can source things from the agricultural sector. We will use those to make engineered materials. We will design products, manufacture, assemble them. Those will go into applications throughout society, agricultural, construction, environment, etc. When those reach the end of their useful life, they will become waste. Waste will also be generated at every point in the process, both obtaining raw materials, transforming them into engineered materials, and then the extent to which we can recycle or reuse those wastes will in large part determine the efficiency of this overall cycle. And with improved efficiency, we not only reduce the externalities to society and the environment, but we quite frequently reduce the cost significantly. When the added factor of regulatory considerations are added, the role of reuse and recycling becomes even bigger, because quite often that is subsidized in many nations and therefore gives us a direct economic advantage. We can look at that material cycle not from just a materials recycling reuse standpoint, but also from an energy standpoint. Energy is very expensive and becoming more so all the time. And so a process or a design that reduces the energetic cost often renders a new product very competitive economically, makes it more resilient to changes in regulatory statutes, makes it more sustainable from a sourcing standpoint, etc. So it doesn't just make it cheaper, it quite often makes it cheaper and more sustainable in the long term financially. So energy costs to consider. Start right with your raw materials. Mining and mineral processing are very energy heavy processes. Most of the raw materials for your chemical synthesis for your polymers start in the petrochemical industry. Sourcing crude oil is extremely energetically expensive as well as just fiscally expensive. So these are all considerations. Primary synthesis is very expensive. For in the case of metals, they are generally not present in their reduced zero valence form in the Earth's crust, and therefore energy is required to add electrons to reduce them from ore, and that is very energy intensive, especially for some of our workhorse metals like titanium and aluminum. Transportation is energetically expensive and is very vulnerable in terms of the type of energy that's required for transportation. Most of the world is still heavily reliant on crude oil for most forms of transportation, or diesel, especially for transcontinental and intercontinental shipping. So that's something to consider, and most raw materials are very, very heavy. So your transportation from extraction synthesis sites to primary and secondary processing can be very energetically expensive. Once you've processed into at least semi-finished parts, that's less so, but we're still talking about things that are relatively heavy in most cases. So some steps might include, ores to refining facilities, your mill products like your wire and rod stock and sheet stock, etc., going to secondary fabricators, polymer resins to formulators and fabricators, etc. We have our processing steps. Most thermomechanical treatments are again extremely energy intensive, especially for our higher temperature metals or for ceramics. Even in our low temperature materials regime like polymers, chemical activation is reasonably energy intensive. depending on the quality of the catalyst you have. Waste remediation is a necessary adjunct to all other steps. There is not a single process that we perform in materials, from raw materials all the way up to use and recycling, that does not generate some form of waste. That cannot simply be released to the environment. It must be treated, and said treatment is necessary and good, generally essential, but energetically intensive in most cases. So, role of recycling. This helps across the board. So if you can design your product to facilitate recycling up front, you will typically gain the benefit of a lot of favorable regulatory status and save quite a bit of money, and basically make your supply chains quite a bit more secure. So in addition to those considerations, just thinking locally, recycling tends to reduce pollution emissions and reduces landfill deposits, and landfill space is definitely a finite resource. Issues with recycling, and we mentioned this with thermoplastic processing. With the exception of your higher temperature materials, metals, and polymers, you will typically get a reduction in material properties, especially again with thermoplastics. Every time you run them through the extruder, you're going to see a reduction in molecular weight. Doesn't mean you can't still use that polymer for a lot of applications, but there's not a one-for-one. So you have to think about, am I recycling or am I downcycling, and plan accordingly. Regardless of whether or not there is a reduction in material properties, products will have to be disassembled. Most products, especially composites, have multiple materials for optimal recycling and optimal retention of original properties. You typically don't want to blend these. If you do blend them going into a recycling process, you'll tend to have to add more energy to do so. So disassembly, shredding, sorting is inherent in the recycling process. And again, we talk about the energy for collection, transportation. That can be high, depending on whether or not it's built into municipal or civil infrastructure and practices. And certainly there are costs up front to do so, which can be prohibitive in some cases. Benefits to recycling. In the metals world, compared to refining raw ore, it's hands down more efficient and generally produces less waste. In the case of certain metals like aluminum, which is incredibly energy intensive to reduce from ore, and in fact is only economically viable in places where there is consistent cheap sources of electricity, primarily from hydro facilities, aluminum is not reduced from ore to any great extent anymore. Recycling is the main feedstock for all new aluminum, with very few exceptions. Ditto with a lot of plain carbon steels that can be manufactured by electric arc remelt in mini mills. Certainly most reinforcement bar for concrete is produced that way. Always a consideration, toxic metals. These are hazardous waste and are treated so by statute in the U.S. under the RCRA 8 regulations via the EPA. Most other nations in the world are equally or more strict with respect to toxic metals. Be prepared to have a very good reason why you need to specify these in an engineering design. Most of them are difficult to reprocess. They will render everything they touch in a process also hazardous waste for the most part. They cannot be added to landfills, so if you're handling these or designing these on any kind of massive scale, they will quickly make your process not cost effective. If you are interested in some examples of this, take a look at the world of the metal plating industry with respect to hexavalent chromium. Recycling polymers. This is where you do have a lot of choices, and this is where thermoplastics, even though they are definitely limited and their thermomechanical properties certainly have an advantage. They are easily recycled / downcycled because they can be remelted and run back through the extruder. Again, be careful about your reduction in molecular weight. There's still sorting required unless you're going for a general polyolefin blend, for instance, then there's less. Thermosets, on the other hand, really they have limited options. They can't be remelted, obviously, because they're continuously covalently bonded and will tend to burn first. You can grind them up and use them for filler. To a certain extent, in some cases they can be depolymerized to make monomer, but you would have to consider the energy considerations of that process and whether or not it might just be better to burn them in a cogeneration plant, which is an option in many places, provided there are scrubbers for toxic emissions, as many of these will emit those on burning. Recycling composites is difficult. You've got an intimate blend of materials, so there's not really an easy way to separate them. Regrettably, if you're going with a polymer-polymer composite like your carbon fiber reinforced composites, it's not easy to separate by simply burning away the polymer matrix and recovering a metal or a ceramic. There are some ways to recover these. I won't go into the specifics. Many of them are very specialized. But they do require special equipment and are not necessarily going to be very cheap from an energetic standpoint. So even though these materials have wonderful unique properties, when you're looking from the life cycle standpoint, always consider what am I going to do at end of life, especially if they're volumetrically intense. If you're building a bridge or you're building a highway or something that's going to generate a tremendous amount of waste at end of service life, what am I going to do with it then? What will be available in terms of options? What's likely to be available at that point, even if it's not now, since some of these applications will hopefully be 20, 30 years away. A little bit of projection. So last slide on a nice hopeful note is the concept of biodegradable polymers. Everyone's probably aware of the floating plastic dump in the middle of most oceans in the doldrums between ocean currents. This has been an issue from the biological world, especially the marine biology world, now for probably several decades, and everyone is aware of the need to have polymers that are sufficiently resistant to microbes and ultraviolet light to survive their service life, but really no more. So when we look at adding things like UV inhibitors and fillers and other protectives into our plastics so that they can survive weathering, something to consider is don't make them too robust. Make them robust enough to survive their service life, and then beyond that point, weathering and degradation by UV and other surface environment aspects is a good thing. We really want these chains to be broken down such that they can be reintegrated into the biological environment and not accumulate. And there's several researchers and other entities working towards introducing some kind of biodegradability in polymers used in weathering applications, have them last as long as they need and no longer. And some examples include plastic tableware, some beverage containers, and golf tees. I suppose since golf tees are out in the environment and probably get lost frequently. Another example is biodegradable mulch films, which you see a picture of there. So being used outside in the environment, obviously, if they're subject to quite a bit of sunlight, de facto, but certainly are produced in massive quantities, as you can see just covering this one single field. And so the ability to have them have a tunable life, possibly based on a certain amount of radiant flux and temperature, would be great. Possibly even have them become a nutrient source that would reduce the need for chemical fertilizer. So there's plenty of opportunities for win-win if we understand the real needs for the service of the service environment and the product, and design for life cycle. So that is it for sustainability. A bit of a philosophical treatment, short, but definitely something that needs to be incorporated at every aspect of engineering in our society today. So thank you for your attention.